All right, hey everyone. So as you can see, we have a bit of a small class today, but that kind of works today. So let's do it. All right. So welcome to day 7 of the decal. So just some quick announcements. The first project is going to be released later today. We finished the spec and we're going to be posting it up on Piazza after this lecture. And the goal of this project is to give you your first major experience with actually doing data science on a real world data set. You'll get to parse out the CSVs, look at the features, do some feature engineering, and pick out what exactly you want to use for your project. And it's also going to give you practice with training a classifier, which will be logistic regression and tuning some hyperparameters to get them Kaggle digits up. So yeah, that'll be fun. That'll be cool. It'll be due sometime around mid-March, March 17th, I believe, the exact date, and a lot more info is on the doc. So once that comes out, then yeah, ask questions from there. But now let's get into the meat of today's lecture, which is logistic regression. But first, let's just do a quick recap of last lecture. So remember that last time we had linear regression. We are taking our weights and multiplying them by our features, and we get out a continuous number. And this works really well for problems where we're doing something like, oh, hey, predicting a house price, miles per gallon, to go off of some examples from the last lecture. But let's say that instead this time we're doing a classification problem. Let's say that we are applying we're trying to make a classifier to predict whether, say, an email is spam or not. Let's say, something like that. And, so for that kind of case, we can't have a continuous number, right? We need something, it's either this or that.
0, 1.
Yeah, 0 or 1.
Or something in between.
So, right. And to do that, we're going to first use this special tool called the Sigmoid Function. It's defined above as 1 over 1 plus e to the negative x. And what's special about this function is the domain of the function is, negative infinity to infinity. So it can take on a continuous range of inputs. However, its output is bounded between 0 and 1. And the reason why that's special is you'll remember. So, we have let's take a look at probability, right? The probability of an event happening is between 0 and 1. That corresponds to from 0 to 100% chance. So what that means is if we take some value along this sigmoid function, we can interpret it as a probability. To give you an example, let's look right here at 0. You see this vertical dashed line? You'll notice that that intersects with the sigmoid function here at 0.5. So that means that there's a 0.5% chance that our x is 0. So, and then, for x greater than 0 and negative, and so the way that we can adapt this is you'll notice that we have this function is continuous, right? But at the same time, it is also a valid probability space. So what we can do is we can actually do a linear regression of this form and pass it into a sigmoid function, which we do over here. And essentially, our theta will correspond to our b's over here. And so we're doing theta transpose x. And then that will be our input into this function over here. And that will give us the probability that our label is equal to 1. As Raul said, we're doing a 0-1 classification where 0 and 1 could be, anything you want. And then similarly, the probability that 0 is 1 minus the probability that's 1, right? It's either, say, spam or not spam, for example. And so this notation right here, h theta of x, is just our sigmoid function for a given set of weights applied to our features. And that's also equivalent to this lower case sigma of theta transpose x. So these are just multiple notations that you're likely to see. So we're going to just expose you to multiple.
Theta tx is just basically, remember last time at the end of class, Jordan kind of went over Okay, given that your guard multiplied by 0.25, or no, guard was negative, it was positive, whatever. Guard was positive, center was negative, right? Remember he was multiplying it by the weights. The way you actually write that in matrix notation is theta transpose x. And then that kind of just does an element-wise multiplication of each of the weights in theta with each of the features in x. Simple math 54. You'll really see that notation everywhere for the rest of your life if you do 189, 127, or anything after that.
Yeah. And so you know, as we said before, all right, and now if we actually look at this graph right here comparing linear regression with logistic regression, we see that, you know, as we said before, linear, the range that your function can take on, it goes from negative infinity to infinity, right? But with logistic, it is bounded between 0 and 1, and you can see over here that this is the case, and it further shows why linear regression by itself isn't suitable for a classification problem. But if we take a linear regression and feed that as an input to this sigmoid function, we get something that is suitable for it. And so, any questions on what I've said so far? All right, I'm going to assume that's cool to move on then. And essentially, what we're doing in math is...
So it gets a little hairy here, so bear with us.
Yeah.
Ask a lot of questions if you get confused by anything in this math.
Yeah, we're going to be doing some derivation. So basically, one thing to keep in mind is that, you know, our features, our training set itself is fixed, right? So therefore, the features and the labels are fixed. So really, what changes these probabilities is, you know, what theta we're using, right? That makes sense? So what we want to do is we want to find some function of theta which maximizes this expression, and in the next few slides, we'll actually get into why it is that this expression works. So get ready for some fun math. So let's just start with this. So essentially what this is saying is, so let's say given our features and what our weights are going to be, what's the probability, given that we have the associated labels that we do in our training set, and it's going to be this expression. Now, let's take a look at why it is that is. So remember that y is between 0 and 1. So let's look at the case when y is 1. So what that means is that we have h theta of x raised to the first power multiplied by 1 minus h theta of x raised to the 0th power. And, you know, anything to the 0th power is 1. So we have h theta of x times the 1 times 1 minus h theta of x to the 0, and this becomes 1, so we're just left with h theta of x. And, you know, we defined our sigmoid function such that this is, by definition, the probability that y is 1. And similarly, when y is 0, then we have h theta of x to the 0 times 1 minus... Well, I'm going to write that figure so you all can see it.
Maybe write it to the right of it. So
Yes. So we have h theta of x to the 0 times 1 minus h theta of x to the 1. And this time, this term goes away, and we are left with 1 minus h theta of x. And again, we defined 1 minus h theta, that is the probability that it'll be 0. So does that make sense to y'all? Yeah, again, this will be getting hairier, so ask some questions. So now what we're going to be doing is, you know, so for our feature set, we have multiple such points. So we want to find the probability that given a certain set of thetas and all of our training points, we get the corresponding set of labels that we do. So we're going to assume that we draw these sample points independently. So the probability that we get all of them is just the product of each individual sample point. And we've shown over here why it is that we have this. So we just have the product of all of our individual points. And so now what we're doing is we're doing something called taking the log likelihood. And essentially what this is so you'll notice that this expression can be a particularly hairy thing to work with. Generally, taking the products of a bunch of things can be very ugly, especially when we're taking the derivative, which we're going to be doing shortly, because as I said over here, we want to maximize this function, right, in terms of theta. And naturally, to maximize something, you want to take the derivative, set it equal to 0. So taking the derivative of a bunch of products can be ugly, but
Like some nasty ass product rule, dude.
yeah, so however, what we can do is we make the realization, so you guys, the log function, right, like log of x, so that's monotonically increasing. It looks something like this, right? And so, we know that if x is greater than y, then log of x is greater than log of y. And so we can use that to then take the log of this expression. So we have I equals 1 to m theta I h theta I 1 minus y sub I. And so if we take the log of this whole expression, so let's first write down some properties of logs. So log, can you guys all see this, or should I write somewhere else? Okay, so log props, log of a times b, log of a plus log of b, and log of a to the b is equal to b log of a. So using these two properties, the first thing we can do is, since we're taking the product of a bunch of things, we can use this first property over here to instead say that it is the log of. It's going to be the sum from I equals 1
I don't think anyone can see that because the.
Alright. Okay. We're gonna bring this over here. Sorry about this. Alright, so we're gonna the sum equals 1 to m of log of h theta of x sub I y sub I plus log 1 minus h theta sub I, y sub I. And now we can use property 2 to bring this yi down. So we can then do y sub I times y sub I to get the expression over here. Does anyone have any questions about this? No? Okay, cool. So you understand now how it is that we get this function in terms of data, which gives us the probability that we have the given labels that we do from a feature vector, a feature matrix, and our associated set of weights. And now what we actually want to do is we want to plug in different values of data in order to figure out from here how is it that we can actually get the right one. And so this is where taking the derivative comes in, and that's why we took the trouble to write it out in this nicer summation as opposed to a multiplication. And that math is outlined over here. And so essentially what we're doing is when we take the derivative, so we have y of 1 minus our sigmoid function minus 1 minus y of that, and taking the derivative with respect to j. So let's see. So, okay. What we do is, if I remember correctly, the derivative of the sigmoid function, so theta prime of x is equal to theta of x times 1 minus theta of x. And using that, we can take the derivative. And so given a specific theta j, so one of our weights in our vector of weights, right? Then we are able to get this. We're able to get this expression for how for the derivative of our likelihood function with respect to a particular theta j, and essentially using that we can make this update rule. And essentially what that comes from is something called gradient descent, where we recognize that we want to move in the direction of the slope in order to reach a local optimum. So let's look at a particular example. Where's the best place to write this?
So the reason why you would use this gradient descent method instead of just taking the derivative, setting it to 0, is that in order to do this, and in order to take the derivative and set it to 0, you have to compute like some matrix inverse, right? Does that make sense to why you'll have to compute some matrix inverse, right? Because you just have some algebra, right, and you'll have to isolate for some x, right? And that's probably going to require you to take some matrix inverse. And that's fine for a very simple logistic regression case where you just have like small matrices. But as you get bigger vectors, like first of all, the cost of taking that inverse blows up. And then when we get to proportional neural networks, which will be like after spring break, you'll see that taking the inverse of the function that a neural network computes is basically like impossible. So instead of what you can do is you can just take the gradient and then just keep subtracting it, and then hopefully you'll reach a point where your gradient is actually 0. I mean, you may not converge to the optima, but like you won't do too bad. So you'll converge to at least like some local minima or something. So
right.
Yeah.
And also just another note that I want to add is that you'll notice that Monday when we did the linear regression, we didn't really have to do something like this, and that's because like with the linear regression we have much nicer properties of when we're actually doing our matrix inversions, and the function that we're taking that is our cost is overall just a much nicer thing. So that's why you'll notice that we have to go through a lot more trouble in math to actually figure out how the heck we find something good. And so to actually give some motivation for gradient descent, essentially, okay, so can everyone see if I write something like over here? Okay, so let's say that I have something simple like y equals x squared. So our local minimum will be over here, right, at 0. Now let's say I start over here. So naturally, if I take the derivative at this point, it's going to be positive. And so what I want to do is then I want to subtract that much, but from our starting point, so we go down, and then if we get to something still positive, we go down further, but then let's say that we cross over somehow to a negative point, then since we're subtracting a negative number, it's like we're adding something, so then we're going to be going forward. And this keeps going until we get to either 0 or we just have some optimal radius, like, okay, we're within this much of 0, so we just decide to stop for the sake of time. And what this constant alpha here is our learning rate. And to give you some motivation, like, remember back when we were children and we would believe like almost anything anyone told us? Or at least I did. But then, as we got older, we got a lot more biased, like, oh, hey, this doesn't conform with what I know. So if alpha is higher, then that means that we take our gradient into account by a larger amount. So for example, if we have a really large learning rate, then if we start over here, we could just jump really fast over here. But if we have a smaller learning rate, we might only jump this much or this much. So hopefully that gives some intuition as to why this term is used and how it can definitely have an impact on how well we are able to converge to a local minimum. Does anyone have any questions? Yeah.
I was gonna say, like, if you choose like a learning rate that's like too high, you may just diverge, right?
Yeah.
Because you also have to think about like what you're doing when you take that gradient step, right? You're not actually following the curve. You're trying your best to follow the curve, right? Like for example, like a parabola, right? If you have like, let's say if you're at 0.11, which is where that shading line ends on the right side. If you take the tangent of that, like, and then let's say you had like a learning rate of 100,000, and you do gradient descent and go in the negative of that gradient, you're gonna end up like all the way down there in that bottom left quadrant. Like you're gonna end up so far from like the actual minimum. So like the gradient kind of just pushes you in the right direction. In theory, if you had like enough training episodes and like a small enough gradient step, like you could just converge to the local optima, like pretty easily. Or you could converge to the local optima guaranteed, but the problem is we'll get into this later. But like if you have a small minima, if you have a small step size, it's going to converge to the local. It's going to converge to the optima really easily. In this case, the optima is the local and the global minimum are the same thing. Later on, we'll see that that's rarely the fucking case. So that's why like you want to have a step size that's big initially, so that if you have something that isn't nicely shaped like this parabola, you want to be able to get out of the local minima and possibly go to the global minima. But eventually, like you want to say, okay, I've probably jumped around enough. I've probably gotten myself out of enough local minimas. The minima that I'm approaching now is probably actually the true global minima, so then I'm going to make my step size smaller and then like convert very accurately and smoothly to the true global minima, which is why like the learning rate will decay.
Mm-hmm.
Is there a way to like try to compute like an optimal alpha to start out with, or is it like pretty much?
To start out with, I'm not sure if there's literature on how to start it out with a good alpha. There's definitely like a lot of theory on like how to compute like an optimal learning rate that changes over time. Actually, there probably is like an optimal like, learning rate.
Right. So
It starts becoming like experimental. Though.
yeah,
It's very experimental, very empirical. Some have like some theoretical guarantees, but like basically like the literature that actually tells you how to do this is like third, fourth year, like PhD, like, or to come up with a new one, you need to be like the fourth or fifth year PhD in like stats or like math or some shit. Yeah.
You can usually do like a hyperparameter search and just try a bunch of different ones all at once because logistic regression is actually fairly fast.
yeah. So you can just yeah, because another thing to mention is that this is all very highly experimental, and often if you like get a new learning rate and you can like do better with it, then that could honestly just be publish worthy. Like, oh hey, in this case we did this, it worked better.
Yeah,
And-
so I mean, machine learning with stats, statistical learning is very mathy, and like you can get some guarantees. As you'll see when you get to neural nets really aren't science yet. They're more like alchemy to chemistry. We're currently stuck in the alchemy phase of deep learning, which is why people just try shit. Like they don't have like an answer. Oh, this will work better than this because of this like theoretical guarantee. They just try shit out and given that this performed better on this one machine learning task, oh, this must be a better solution. So yeah, deep learning and neural nets is kind of like what alchemy is to chemistry.
But it pulls out cool stuff. So it's
It
not,
gets cool shit.
it's not entirely pseudoscience.
Mhm.
Yeah, it's kind of like, you get a little bit of gold from your lead. It's not bad.
Right. Oh yeah, and so just another thing that I wanted to mention really quickly about this learning rate is that, as we kind of hinted before, it can change over time. Because, again, going back to the example of us, we're more likely to believe things when we're young, but then over time, like, we become more skeptical, so that would correspond to a learning rate changing. And that makes sense when you think about this example, because the closer you get to an optimal solution, you just need to go, like, maybe a little bit more. You don't want to wildly change just based on one example. So that gives some intuition about that. And actually, just another thing that I wanted to say about logistic regression in general is that you'll notice that we kind of made this assumption that, okay, if something is, like, say, greater than 0.5, then we can interpret it as being a 1. If it's less, we interpret it as being a 0. But one nice thing is, because we actually have access to the output probability, we can actually change that to suit our needs. And to give an example of how this might be the case, let's say we're making a classifier to diagnose whether someone has cancer. If we look at the risk of a false negative versus a false positive, clearly it's better to tell someone that they may have cancer when they don't rather than the other way around. And so because of that, we can actually change our value. Oh, like let's say maybe instead of 0.5, we could make it 0.45, 0.4 or something to suit our needs. So that's something that you're able to do with these output probabilities. Just wanted to like let you guys know and like to give you that kind of tip of, oh, like sometimes a false negative isn't necessarily as bad as a false positive or vice versa. So that's just something to look at on a problem by problem basis. And the next thing that we're going to be looking at is the issue of multiple classes. And so because, before we were just saying, oh, hey, is this a 0 or a 1? But let's say you look at the MNIST dataset, which is a dataset of handwritten digits, and you want to figure out what digit each thing corresponds to. There are 10 different digits. So in that case, we have 10 different classes. And in general, you could have a wildly number of different classes. So the question now becomes, how do we handle this? Well, the easiest way to handle this would be what's known as a one versus all type regression. And essentially what that is you say, what's the probability of something being, in the case of our digit example, a 0 or not 0, 1 or not 1. And so essentially it's like we're running 10 separate regressions, and we look at those and figure out which one will, and we have like 10 separate probabilities, each one corresponding to one of our digits, or more generally, if we have k classes, we have k different probabilities, and then we can normalize them. And
There's also another method called 1 versus 1, which is instead of doing like, which you will still get like a list of like probabilities. The difference is, though, the way it's computed is instead of saying, is this a 1 or not a 1, what it does is it says, like, is this a 1 or a 2? Is this a 1 or a 3? Is this a 1 or 4? Is this a 1 or 5? Is this a 2 or 3? Is this a 2 or 4? Is this a 2 or 5? And essentially, it just computes, instead of 10 functions, as you would have done in the 1 versus all, it would compute 10 by 10 function. 9 by 9? I don't know.
Like
9
k
by 9.
times k minus 1 over 2. That many?
Yeah, sure. Combinatorial math, guys. CS70. But yeah, so that's the other method of doing it. It has some nice properties to it, and like I won't really talk about it, but it's kind of like a voting method. So you kind of just basically like count like all the instances of like what it says it could be. Like if it says it's a 1 versus if it says it's in the 1 versus 3 case, if it says it's a 3, then that's 1 vote towards 3. If it's in another case, in the 2 versus 3 case, it votes for a 2, and you kind of just do like all these votes, and then at the end, like divide by like the total number of like combinations, and you'll get some output probabilities.
Right, exactly. So yeah, that's one way of doing it, and another way of doing it is just 1 versus all. You know, you get k probabilities, and then you normalize them. The way that we do that is we apply this sort of function, and essentially what this is saying is, so again, if you look here, theta transpose times x, we are still doing the same sort of feature times weight multiplication thing that we're used to and have been doing before, but this time we apply what's known as the softmax function, and essentially what that does is we do, we're doing e to the x over the sum of all e to the I for like every I in our classes, and this means that then whichever one is the biggest that's what we're going to say it is. Does anyone have any questions about this? Yeah?
Sorry, can you just explain that again?
Yeah, so essentially what we're doing is, first we're doing theta transpose times x. That's the same sort of thing that we've been doing before. But now what we're doing is, so for all of our probabilities, we're applying this thing called the sigmoid function, the softmax function. So to write that out again over here, that's, so softmax for a given class I. I'm going to write that here. So softmax of I is equal to e to the I over the sum of e to the j, where j is essentially all of our different classes, right? And so clearly, this, we can interpret this as being the sum total of all of our, this is the sum of all probabilities. And therefore, we can that allows us to interpret this as a valid probability. Does that make more sense? Is anything still unclear?
I think it makes more sense.
Okay. Anyone else have any questions? Anything that was unclear you want me to explain again? Something like anything? Okay. So also, in order to give some more explanation, so this process over here of maximizing given our features and our weights, this is called maximum likelihood. If you want to look it up more on your own, it's a general approach that you can apply to solve many different kinds of problems, given what your specific probability of a label given your features and weights are. Mm. And so, and again, over here, this is what's known as gradient descent. But this is the standard method of computing it. Given the derivative with respect to a given feature, you update it as we were doing over here. But there are other methods which, especially when we'll get to neural nets, we see we use more because this method can have a slow convergence rate. There are many methods which can have a fast convergence rate. So we'll cover that more in neural nets, but if you have any other questions about that, you can come talk to me in office hours on Monday, look stuff up, and then maybe ask questions about what you see, or just come to office hours and ask me. We can go over other different methods, and yeah, that was pretty much all I have in terms of a lecture for understanding logistic regression, the math behind it, and there's a short IPython notebook that I uploaded to the GitHub, which is basically just about playing around with different multi-class kinds of classifications and giving you a sense of how to call it which will be useful for the project, So if you have any questions, so then once you're done with that, I'll actually upload the project right now. The quiz is probably up, so you can take a look at that.
Did we put the slides? Hey Daniel, do you know if you link the slides
On the
website? For time? Can you do that now? Yeah.
Yeah, so, yeah, Phil, you put the quiz up, right?
Yeah, the quiz. I don't think the slides are posted anyway. Though.
Yeah, those permissions denied.
Wait, shoot, okay.
Permission is denied.
Wait.
Just fix that now.
Yeah, let me just fix that right now. And then, you can start, looking over the project, maybe you can start forming your own groups in here. And then if you have any questions, you can, ask me or ask us.
It's really more like a